In this lecture, we look at the IRC of transcendental functions. In the previous lecture, we learned to compute the derivative, or the IRC, of powers of x to the n for various values of n, and this allowed us to differentiate polynomials. However, many of the functions used throughout the sciences are not polynomial functions, but are transcendental functions. These are functions involving trigonometric functions, exponential functions, or their inverse functions, such as the logarithmic function, which is the inverse of an exponential, the arcsine and arccosine and arctangent functions, which are inverse trig functions. The functions f of x is sine x and f of x equals cosine x. Sine x and cosine x are the functions I want to try to differentiate in this lecture. These functions are continuous on the real line. And so the limit of an expression involving sines and cosines can often be found just by plugging in, by substitution. This becomes more complicated, though, if we try to look at limits of functions involving ratios, such as a tangent function, which has a cosine in the denominator. In an earlier lecture, we proved two limits. We showed that the limit as x goes to 0 of sine x over x is 1, and the limit as x goes to 0, or theta goes to 0, of cosine theta minus 1 over theta is 0. We have these two limits, both involving a denominator going to 0. We need these when we compute the derivative of the sine function. Using the definition of the derivative and a sum of angles identity, we can do this. If my function is the sine function, then by the definition of the derivative, or the instantaneous rate of change, we have that the instantaneous rate of change is the limit as h goes to 0 of the rise over the run, sine of x plus h minus sine of x over h. By a sum of angles formula, I can write sine of x plus h as sine of x cosine h plus sine h cosine x, and therefore the numerator becomes this expression, and the denominator is still h. Once I have this expression, I can break my fraction into two pieces. I can think of the one part being sine of x cosine h over h minus sine of x over h. That's the first part. And the other part was that middle term, sine h cosine x all over h. If I break up my fraction into two pieces, being very careful with it, I can then find a way to get rid of that h in the denominator using the limits we had earlier. In the first term in this sum, I'm going to factor out sine x, and in the second term, I'm going to factor out cosine x, so that I get this expression. The derivative is the limit as h goes to 0 of something here times sine of x plus a limit times cosine x. But we know these limits. The limit of cosine h minus 1 over h is 0, and the limit of sine h over h is 1, as long as we're using radians. And so the derivative of the sine function is 0 times sine of x plus 1 times cosine x, which is just cosine x. So the derivative, or the instantaneous rate of change, of the sine function is just the cosine function. We can also compute the derivative of the cosine function. There are several ways to do this, and later in the course we'll look at complementary trig functions and redo this derivative, recognizing that the cosine is the complement of sine. But until then, one way to do the derivative of the cosine function is to write out the definition. The derivative is the limit as h goes to 0 of change in y over change in x. The change in y in the numerator is the cosine of x plus h minus cosine of x, and the denominator is just h. Using a sum of angles identity, we can then rewrite cosine of x plus h as cosine x cosine h minus sine x sine h, and so get this expression. And then, as we did before, I can do a little bit of factoring. I can pull out cosine x, and it's multiplied by cosine h minus 1 over h, and I can pull out the sine x and get sine x times sine h over h, and again, we know those limits, and so plugging those values in, we get minus sine x. So the derivative of cosine x is minus sine x. In summary, we found the derivative of two important trig functions. The derivative of sine x is cosine x. The derivative of cosine x is minus sine x. The typical functions showing up in the sciences are the polynomials, rational functions, trig functions, inverse trig functions, exponential functions, and their inverses, the logarithmic functions. We'll look at inverse functions later, but to complete our understanding of derivative, we need one more derivative, one more IRC. We need to look at the exponential function. To compute the derivative of the exponential function, we again take the limit of the delta y over delta x. My function is e to the x, so f of x plus h is e to the x plus h. And so we have e to the x plus h minus e to the x is the rise over the run h. I can use properties of exponents to write e to the x plus h as e to the x times e to the h. We can factor out e to the x and write this expression. And then this limit, as h goes to 0, of e to the h minus 1 over h is something we've seen before. Earlier we discovered that, or demonstrated that it was equal to 1. And so the derivative of my function e to the x is just 1 times e to the x, or e to the x. The derivative of e to the x is e to the x. This result explains the importance of the element e in mathematics and the importance of the exponential function. The exponential function e to the x has the property that its rate of change is equal to the function itself. That is, the derivative is equal to the function. Just as an aside, to be proven at some other time, it so happens that if b is some real number greater than 0, then the limit as h goes to 0 of b to the h minus 1 over h is the natural log of b. If b happens to be e, we're going to get 1. If b is something else, we get the natural log of that base. Here, ln is the natural log or log base e. And that translates into the following fact that we'll use later in the semester. The derivative of any exponential function is a multiple of an exponential function. If the base is b, then the derivative of b to the x is the natural log of b times b to the x. And we'll get back to this at a later time. At this point, we have the following derivative rules. We have the power rule that tells us about polynomials. We have the derivative of two trig functions. We have the derivative of the exponential function. And so we know the derivative of some basic transcendental functions. In the next part of the course, in part 2, we'll develop more derivative laws with the intent of computing the derivative of almost any function.